Good day. This is our presentation for EKC222, Chemical Engineering Thermodynamics. We are Group 10 and will be discussing the topic of heat capacity. In the 1760s, Scottish physicist Joseph Black introduced specific heat, distinguishing the heat required to raise the temperature of different substances. His experiments with melting ice and boiling water led to the concepts of latent heat and specific heat capacity. Early understanding of heat, 17th to 18th century. In the early days, ancient Greek philosophers like Empedocles and Aristotle viewed heat as elemental, based on qualitative observations without measurements. Moving into the 18th century, Antoine Lavoisier introduced the caloric theory, suggesting heat was a fluid called caloric that flowed from hot to cold objects. Though incorrect, this idea laid the groundwork for quantitative studies of heat. The 19th century saw a paradigm shift with scientists like Julius Mayer and Hermann von Helmholtz linking heat to energy. This led to the first law of thermodynamics, showing heat capacity relates to energy in molecular motion. The turn of the 20th century brought more sophisticated theories, including Albert Einstein's application of quantum theory to heat capacity. Albert Einstein applied quantum theory to heat capacity, explaining why specific heat decreases at low temperatures. This advanced understanding by connecting heat capacity to quantized energy levels. Einstein's quantum approach helped us understand heat capacity variations. In 1912, Debay's theory improved predictions by modeling atomic lattice vibrations. Quantum mechanics now allows precise calculations of heat capacities based on atomic structures. Our recognition of heat as energy in transit was preceded historically by the idea that gases, liquids, and solids have capacity for heat. The definition of capacity is to measure the amount of the heat required to change the temperature of substance by certain amount. For the specific heat capacity is the amount of heat required to raise the temperature of 1 unit of mass of a substance. Heat capacity at constant volume CV can be defined as the change of internal energy with respect to temperature. The above is a derivation of the heat capacity at constant volume. Heat capacity at constant pressure is defined as the change of enthalpy with respect to the temperature, and above shows derivation of enthalpy change equations. The relationship between Cp and Cv for an ideal gas can be derived by using ideal gas and first law thermodynamic equation. After derivation, we obtain the equation of Cp equals Cv plus R. Next is about the specific heat of an ideal gas. For ideal gas, specific heat capacity is independent of temperature. Monoatomic, diatomic, and polyatomic gas have different specific heat capacities. Heat capacity at constant pressure changes with temperature and is often represented as a polynomial function of temperature, effectively capturing temperature-dependent behavior in many materials over a specific range. In applications like water heaters, heat capacity is key to understanding energy requirements for heating. For water, specific heat capacity determines the energy needed to raise its temperature by 1 degree Celsius. How to calculate changes in specific heat capacity against changes in temperature using application, MATLAB. To calculate the specific heat capacity of air as it changes with temperature in MATLAB, we start by defining a temperature range from 300 to 500 Kelvin. Next, we set the constants A, B, C, and D based on empirical values for air. Using the equation shown in the MATLAB coding, we can calculate Cp across the specified temperature range. Then plot Cp against temperature, giving us a clear visualization of how air's specific heat capacity changes with temperature, all without needing manual calculations. Let's solve this question using MATLAB. From this question, we need to calculate the heat and work requirements and the changes in internal energy, ΔU, and enthalpy change, ΔH, of the air for cooling at constant pressure followed by heating at constant volume. Assume the gas has a molar volume of 0.0227 cubic meters per mole at 0 degrees Celsius and a pressure of 1 bar. First set all the variable that we have. Then calculate the initial and final volume calculations. For the first process including constant pressure cooling, this is the calculation for change in enthalpy, but it should be 0 since the temperature is constant. Then calculate the work done in the first process. Label work done in process 1 in heat, Q1. For the second process, which the volume will be constant, calculate the change in internal energy, but it should be 0 in this case. The work done will be 0 for the constant volume. Variable Q2 will be equal to internal energy. This is the overall equation to calculate total heat, total internal energy, total enthalpy, and total work. followed by using a command to display the result for each of them. This will be the final result shown. Questions? Leave a comment and I'll be glad to help. Thanks for watching.